Alrighty, folks. Looks like it's 1 o'clock. Time to get ready for our next live stream here. So, in this live stream, we are looking at the concept of graphing and linear relations and rate of change. Again, during the live stream, if you need to ask a question, you can send me a message in the chat, or you can send me an email or a message through Edsby, and I can try and answer those questions. Again, you can send me messages through Edsby or email at any time if you have questions regarding this live stream or any other topic from the course. But let's get started and take a look at graphing linear relations. So linear relations, there's different ways to represent these. We can represent them as a set of ordered pairs. So do note there is an x and a y in each case. So this is an x value of 5, a y value of 4. These are points that can be plotted on a graph, and we are separating each set of brackets with commas. I don't necessarily love doing it this way because it gets confusing with so many brackets and commas. It's not as easy to follow. Where if you take something that is very similar and make a table of values or a t-chart, you can set up your pairs this way in a vertical manner. So you'd have your x and y value. These could be converted to 0, 1 in brackets, 1, 6 in brackets, 2, 11 in brackets. And that looks a lot neater and easier to follow and read than the ordered pairs method. But it is important to understand what ordered pairs are and that they are giving you an x and a y value in each case. Now, the next way of representing linear relations is using a graph. And you can draw a graph of a line. So any linear relation is going to be a straight line. Okay, so no curves. In later grades, you'll look at curved lines and that. But in the case of linear relations, we're looking at a straight line. You should be able to draw it with a ruler and a ruler on one direction. No bends or anything. And then the last way of representing it is using an equation, and our equations are generally set up something like this: a y and an x. We need a relationship between the y and an x. Table of values has a y and an x. The graph has a y and an x axis. The ordered pairs have a y and an x value. So here we have a relationship that every y is equal to the x value times 4 plus 2. So that is our equation method of showing it. So now we want to take a look at some questions from the book here, from the linear section. That's a 4.1 section. So if we take a look, we're going to start with number 2. Let me make sure this is showing here. Textbook. There we go. Transition that over. There we go. So the questions here. Number 2 is what we're looking at. And let me zoom in a bit there. There we go. So a bathtub is being filled with water at 8 liters per minute for the first 5 minutes. Create a table of values and a graph to represent the volume of water. And then we'll look and see if this is a linear or non-linear relation. Explain how we know. And then determine how much water is in the bathtub after 9 minutes. So if we switch over to my notes here, I've already pre-set up a lot of these questions just to save us some time. Otherwise, we could take a long time with some of these. These do take longer to do, creating the table values, especially when you're trying to draw the graphs. It does take a little more effort. Again, recall you could use a little piece of paper turned perpendicular to set up your grid lines, and you can make yourself a nice graph. Or if you have access to a printer, you can print off some grids. If you look online, you can find a lot of different styles of grids out there. And or if you have graph paper at home, that's even better. But if you're in like my case, where I just have some line paper here, you can turn that line paper perpendicular. All right. So looking at this one here, we were filling the bathtub 8 liters per minute for 5 minutes. So I set up a t-chart. The time is what we know is going to be consistently moving forward at 5 minutes, and then our rate. Okay, this is something that is changing. This is a rate proportion, or sorry, a relationship of 8 liters per minute. So that relationship is going to be the second value. So our time here, 0 minutes, 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes. Why did I pick that? Because we know we're filling the tub for 5 minutes. So then our volume in each case. So after 0 minutes, there should be no water in the tub. After 1 minute, we've filled up 8 liters. And then every minute after that, we'll add another 8 liters on. So we're just increasing by 8 liters each time. So the next time would be 16 after 2 minutes. 3 minutes will be 24. 4 minutes will be 32. And then after 5 minutes, we would have 40 liters in our tub. So there's our table of values filled out. Again, we just said that at 0 minutes, there'll be no water in the tub, and then it is increasing by 8 liters per minute. And we are going up by 1 minute intervals. So now if we want to graph that, what we do is we take our t-value, which would be along the x-axis, or in this case I'd label it the t-axis, and then our second value, our changing value here, goes on the vertical axis. So I have set up the graph, and then I'll just plot these points. I got a point at 0 and 0. So there's a point right here at 0 and 0. When t equals 1, v equals 8. So up here at 1 and 8. When t equals 2, v equals 16. So 2 and 16 match up here. 3 and 24 is my next pair. That matches up right here. So I'm just matching those up each time. The next one here, we have 4 and 32. So again, we're just matching up these points on the v and the t axes. And then 5 and 40. And we match those up right there. So now I can connect my dots. And try and get right through the dots here. Just making my line a little thicker. There we go. So there's my my graph, and I could extend this beyond. We don't know how big this bathtub is. They may have just stopped in 5 minutes, but they may have kept filling the tub. It just says for the first 5 minutes, so they could continue on. So technically, this graph could extend past that, and we can get more values out of it. Like at 6. So now I know I can actually read this graph and look and say, hey, at 6 minutes, it's going to have 48 liters in the tub. So I can use that graph to help me find some additional values if I make it big enough. So now the next portion of this question had asked, is the relationship linear or nonlinear? And explain how you know. Well, it's a linear relation because all our points graph as a straight line. So the points graph in a straight line would be a good explanation there as to why it's a linear relation. So it is linear. Now, part C had asked, explain, looking at the wrong one here. 2, ABC. How much water will be in the bathtub after 9 minutes? So after 9 minutes, well, we only went up to 5. But we keep going up by 8 liters each time. So there's a couple ways I could do this. If I had a bigger graph, I could extend this graph up to 9. I didn't do that. I mean, I have the room to do it, but I could do that. Add a couple more lines and figure out where that is. I could extend my table. So I could do 6 and 48. And then I'm just going to shift my table over here. V, 7, 8, and 9 for the times. So this is just shifting the rest of that t-chart over. And then from 48, we'd add 8, and we would have 56. And then we'd add 8 and get 64. And then we would add 8 and get 72. So 72 liters would be how much water is in the bathtub after 9 minutes. Another way to do this is if you recognize that it's 8 liters per minute, so each of these is just the number of minutes. 1 times 8, 2 times 8, 3 times 8, so 9 times 8, which is 72. That's another way of calculating that as well. So there's multiple ways. Because there's multiple ways of representing linear relations, there's usually multiple ways of finding the solution. All right, now the next one I want to look at is question number 3. And so question number 3 here relates back to number 2. So the bathtub in number 2 can hold 140 liters of water. We want to make a table of values and a graph to represent the unfilled capacity when the bathtub is being filled at 8 liters per minute. So in the last question, we were measuring how much water was in the tub. Now we want to know how much empty space is in the tub. So the opposite. So in this case here, what we have is that the water, our table here, at time 0, when we start, the bathtub's empty. There's no water in it, so it can fit 140 liters more still. And then every minute, it's going to fill up with 8 liters of water, so there's going to be 8 liters less space. So we're going to take away 8 each time here. So 140 minus 8 is 132. And then we'll take away 8 again, and we'll get 124, and then 116, and then 108, and then 100. So I just set it up with the same 5 minutes we had done before, so we can make a comparison type of graph here. I laid out my graph the same type of size. So each time, if we look at a comparison of our volumes, this is how much water's in the tub at any point in time. This is how much water is draining out of the tub at, this is how much water's coming, or is left, how much room is left for water, how much open space, how much air is in the tub at any time. So now we can graph that. So this one here did a broken graph and just counted down from 140 here. And so I got 0, 140, 1 and 132, 2 and 124, 3 and 116, 4 and 108, and 5 and 100. And there's my graph. I can't extend this one in this case. And the reason why not is that it's a broken graph. If I extend it, I got 6 and 0, which isn't true. This isn't it. After 6 minutes, it's not going to be full. There's still a lot of room left here after that. It's only going to be at 192. So with a broken graph, I have to stop the graph there. Unlike this one, where we could keep going because it's not a broken graph, here it is a broken graph. We have to stop it from going down. So the next part of that question, after we did that, said to compare the graphs and explain the differences. So if we pull out here a little bit, here's our 2 graphs. So both graphs kind of have, like, if you were to connect these, if I was to take my page and fold it, these are actually at 90 degrees. And actually, if I was to just extend these lines, I'm going to extend these lines back here a little bit. And this isn't something we normally do. It's just the way I laid out my graph paper here so that we could show this. But if we extend that back, this would be a 90-degree angle. And if we put these graphs side by side, like touching each other, they'd be at a 90-degree angle to each other since we're using the same scale. So these graphs are actually the same steepness, just one's going up and one's going down. So the graphs are actually very similar in that nature, except that one is going up and one's going down. So this graph is what we would call increasing, and this graph is what we'd call decreasing. So the first graph is increasing from 0. And that's important. It actually starts at 0. And that's an important concept we'll look at in one of the later lessons. In the next case here, though, the second graph is decreasing, not from 0. And I'm focusing on that 0 because, again, that's going to be it's an important concept later on. You could say it's going down, one's going up, but the proper nomenclature is to say that it is increasing. So we have an increasing graph on the upper one, and then this lower one here is a decreasing graph. And that point of 0 is important, and you'll see that later when we're creating equations and things like that with these. All right, so one more question from this section that I wanted to look at was number 6. And you may notice in the textbook that some of the questions are titled Achievement Check. And so if I switch over to that, actually, give me a second here. These ones don't show solutions in the back. If we were in class, this would be something that you'd be asked to do this question and hand it in so we can check how you're doing. And so you can't just take a look at the answer in the back. So I'm making sure that I take up these achievement check questions when I assign them. But we'll take a look at this. So I've pre-filled out a lot of the information here just because it's very similar to the previous question. But what we have here is that we have Maginder's electric hybrid car has a fuel efficiency rating of 3.5 liters per 100 kilometers. Minyi's sedan has a fuel efficiency rating of 7.5 liters per 100 kilometers. Each trip begins with 40 liters of gas. Make a graph to show the fuel remaining versus the distance traveled for each car, putting them both on the same grid. Are they linear relations? How are they the same? How are they different? How much fuel remains after 500 kilometers? So I've got this all set up for us here. I've already done the two tables of values for us. So the first guy was 3.5 liters per 100 kilometers. So I just went the distance up 100 kilometers, going up to 500 here. The 6 values is a good number. Make sure that we have a good number of values to create a graph. It also happens to be a number that we need later on in the last part. So each case here, it starts with 40 liters, and then every 100 kilometers, it's going down by 3.5. So each of these is just minus 3.5, minus 3.5, minus 3.5. In the next case, similar, except it was going down by 7.5 each time. So again, we started with 40 and just went down by 7.5 each time. So now if we go to plot these on the graph, I'm going to do this first one here in red and the second one in blue. So I'll plot my points. 0 and 40 is my starting point. And now I'm not going to be perfect with my graphs because they're with the decimals, it might not be as easy, and these in-between values are not right on the grid lines, unfortunately. However, we'll do our best to graph these to the best of our ability. I can pretty much guarantee if I put this point here, just because I know this is right in between the lines, that the rest will kind of line up here. And so I'll cheat this graph a little bit so that it looks good. So it's going to fit on this line here. You actually only need 2 points to make a line, but the rest should fit in there. 136.5 would be about right here. 233. Now I know this is a linear relation, so it's about right here. And see, it's not quite lining up well because, again, I'm hand drawing this graph. 329.5, so again, that would be about right here. And then 426, again, right about here. So my points aren't lining up perfect, as you can kind of see here. Actually, this one's a little skewed. It should be over here. So I misplaced that. If you ever misplace a point, just put next to it, and that'll note that it's not there. So you see my points are pretty much in a line. They're a little off because, again, my graph is probably not perfectly drawn, but it will make a straight line like that. So there's my red graph. And then same idea with my blue graph, my second graph here. Start at 40. 410, that's a nice easy point. So I know it's going to hit that point right there. 225, just going to put these easy ones on. And then I know the rest kind of fit in between there. So it'll be looking something like this here. And then the rest of those points should pretty much fit if I did everything right. 32.5, that looks pretty good. 17.5, that's pretty close there. And then the 500 should be at about 2.5. And so those look pretty good. So that one worked out pretty good there. So there's my 2 lines graphed up. Again, cheated a little bit. Again, you only need 2 points. So if you know it's a linear relation, then we're good. In this case, we're testing that, but I'm going to tell you that it is. How do I know? Because they make straight lines. So how do we know? Part B said, are these linear? And then the answer there would be yes. They both graph straight lines. Straight lines. All right, and then in part C, it says, how are the relations the same? How are they different? So both in the sameness category, both decrease from 40. Something like that. They're both started at 40 and they decrease from there. In the case of different, the blue graph decreases faster. So this is actually when we use that term of slope, this has a steeper slope. This slope here is not as steep, so this is a steeper slope, but they're both decreasing, they're both going down. And the last part, D, says how much fuel remains in each car after 500 kilometers. So there's our answers for D right there. All right, now I wanted to, again, get through some of these concepts a little quicker, so we're going to do rate of change as well, which is 4.2. So a quick look at that. Some key concepts for rate of change. The rate of change is calculated by figuring out the rise and run of the graph. So the rise is this portion here, going up and down, and the run is this portion here. This is called a rate triangle. And so you can draw it here. You can draw it underneath as well, this way. And so the rise and run, we always read it from left to right. So we always start at the leftmost point and go over to the right. And the the run is always going to be positive then. It's always going in a positive direction. You know, this could be going from like 1 to 4. But in the case of the rise is only going to be positive if the graph is going up, if it's increasing. So in this case, the rise would be a positive. It's going from like -1 to 5 or something. But in the case of something like this, where you have a graph, let's do some colors here. Here's my grids, and then my graph line here. This graph is going down, so the rise from left to right, the rise is going to be negative because it's going to go from a higher number to a lower number, so it's got to be going down. So important concept to keep in mind as the graph is going down. If something's decreasing, looking back at these would both have a negative rate of change because the graph is going down. And again, we also use the term slope, as I mentioned earlier with that. So now taking a look at a couple problems here. Made this one really big here. Try and fit it on the screen as best I can. So this here is number 1. And so we'll switch over to the questions here. So the question for number 1 says, when you record a typical 1-hour television show, you can use 1.1 gigabytes of storage space. Make a table of values and a graph to represent this relation up to 10 shows. And then we'll draw at least 3 rate triangles, figure out the rate of change, see what it represents, and then how much more storage space is needed to store 11 shows, and show how we know. So Again, I made our table of values already. Same process as before. We needed 0 to 10 shows, and then we started at 0 gigabytes of data, and then this is 1.1, and then we just added 1.1 each time as we went up. So now I got this big giant graph here, and I'll plot these points out. We'll use blue for this one. And again, I'm not going to be able to graph these perfect right on because they are decimal numbers, which is why I kind of made it a little bit bigger like this. But it would work perfectly fine with a smaller graph. So 0 and 0, and then I'm going to pick some of these easy ones like 10 and 11 would be up here. And I didn't quite fit it well. Again, probably should have drew this graph a little better. But there, somewhere up there. And then 5 was 5 and 5.5. So there's some points that'll line up. And again, I'm just trying to do these fairly quickly. You can put all the points on. If you draw a better graph than me too, that would be awesome. But I just want to get through the concepts here. So there's my graph. And again, those points, if we were to double check, it's about 2.2 there. It's about 3.3 there. So it's looking pretty good. My grid lines are not too bad. Now, what it wants us to do is draw ourselves some right triangles. So when you draw the right triangle, pick grid lines that you can read. So some people I'm just going to pick any point on the line here. I'll just pick this point right here. But this point right here, you can't really read where that is. We can't read on here what value that's at. We can estimate what it is, but we might not be accurate. So pick good points where you see, oh, right here, okay, that looks like it's crossing a grid line. So this right here, crossing on the grid lines, and so all three lines are intersecting, that's a good point right there. And then I'll follow along, and actually this right here, 0, 0 is a good point. So there, I can draw a right triangle. I'm just going to make it really thick here. So there's my right triangle. And my rise is going up 1.5. So I've gone from 0 to 1.5. So the rise is 1.5. The run here goes from 0 to 1.5. So it's about 0, 1.5. Now I can draw another right triangle, and they don't have to be small. They can be big. I can actually go from 0 all the way over to 5 and up to 5.5. And here I'm drawing one underneath. Again, it doesn't matter. You draw it above, you draw it below, as long as you're making a right angle triangle. Okay, it does have to be a right angle. Follow those lines. So my rise in this case is going from 0 up to 5.5. So my rise is 5.5. My run goes over from 0 to 5, so it's 5. And I'm going to draw one more right triangle here to get that third one in. And I'm going to do this one here. So I'm actually going to do this very last from 5.5, because again, perfect intersection of the lines here. And then I'm going to go up to here. Now again, the more accurate your graph, the more accurate your answers are going to be, which is why we often use formulas and things like that as well as graphing. This might not match up as well as this does. Actually, I know it won't, so this one's a little bit off. But these two I know are going to be good. But we're going from 5.5 over to 10. Or sorry, we're going from 5 to 10. Sorry, my mistake. Going from 5 to 10 along the x-axis here. So this is increasing by 5. So we're running over 5. And then we're going from 5.5 up to 11. And that is an increase of 5.5. So there's my rise, there's my run. There's my rise, there's my run. So now it asks us, so that's part B. In part C, what's the rate of change? Well, the rate of change is equal to the rise over the run. And so that would equal the rise of 5.5 over the run of 5. So my rate of change is there, and my units in this case, it was, this is the number of shows, and this is the gigabytes. So we can calculate a unit rate now. I can do 5.5 divided by 5. That's going to give me my 1.1 gigabytes per show. And if you go back to the question, 1 hour of television show uses, so 1 hour is 1.1 gigabytes. That's the rate of change. They gave it to us in the question. All right. I wanted to do one more quick just summary question here. Just to get a couple concepts, more talk about it than do much work, and then we'll be that'll be it for this one here, and that's number 7. So question number 7 here: a web designer charges $200 plus $75 an hour to design a website. What number is the rate of change? Well, a rate again has that division. It's something that's changing over a course of something else. So $75 every hour, that would be the rate of change. So our question here, what's the rate of change, would be $75 an hour. Calculate the cost for a website when it takes 5 hours to design, 8 hours to design, 12 hours to design. What we do in each case is multiply the hours by 75 and add 200. And here you could actually make an equation. So in here, really quick, for number 7b, you could make yourself an equation. It would be the cost equals the $75 times the number of hours plus the time. So that would be the general kind of equation, the relationship. The cost is equal to $75, the rate right here, and then the standard 200 that he charges. So you can figure out each of those by subbing in 5, 8, and 12 respectively. The next part says calculate the rate of change between 5 and 8 hours and between 5 and 12 hours. So the rate of change would be the change in that. But really what it is, they've already given us the rate of change. That's the change per hour, 75. So you'd calculate the rate of change between those, and you'd find that because when you calculate them, you're going to get, and I'll show you here quickly. So 5 hours, the cost after 5 hours is, that's not a 1 over, 75 times 5 plus 200, 75 times 8 plus 200, and 75 times 12 plus 200. And so we can calculate each of these costs. And so in each case, we would have $575, 75 times 8 plus 200 is going to give me 800, and then 75 times 12 plus 200 is going to give me 1,100. So between 5 and 8 hours, so the rate of change here is the money over the time that it's taking in general. And so between 5 and 8, the change in money is 800 minus 575. So the money's gone up by 225, and the time has gone up by 3 hours. In the case of 5 to 12, it's gone up. The money has gone up by 525, and the time has gone up by 7 hours. And I think I did that right. Let me double check that. 1 0 minus 575. Yeah, Yeah, so that looks good. So if we change these to unit rates, 225 divided by 3 is going to be 75, and 525 divided by 7 is going to be 75. They're both going to be 75. The rate of change is always going to be the same in a linear relation, and that's the important thing to note here, is that whenever you have a linear relation, you're going to have a consistent rate of change. Okay, so that is the two. This was a little bit longer again. We're trying to get through some of these concepts together, and make sure the linear relationships is one of the major concepts that will carry through into grade 10. So it's important that you get a good handle on it. Again, if you have questions, send them to me through Edsby, send them to me through email, and we'll see you next Wednesday.